Hello everyone, I'm Andre Falco and it is a big pleasure for me to share some of my Flink experiences with you today. My journey with Flink started more than 3 years ago when I worked on Lyft's pub subteam. I helped make the integration of Flink to Kafka reliable and learned from amazing Flink contributors and users what it takes to keep critical Flink applications running 24/7. Later, I worked at Stripe where I took on the challenge of improving the reliability of the Flink platform. I recently joined Salesforce, where I'm observing a recurring theme. Developers discover that Flink applications unlock important capabilities, the company and its users start to depend on these capabilities, and then Flink operators wind up having a rough operational time keeping data processing flowing. This talk aims to show you a technique called fault tree analysis so that we can switch to being proactive versus reactive. Before I begin, I must share the following disclaimer. I've been practicing my speed reading, so set your timer in 3, 2, 1, done. Just kidding. In a nutshell, don't take any info from this talk as investing advice. This presentation first walks you through a couple of use cases where Salesforce leverages Flink. We'll set the tone and express how we go about setting user-facing service-level objectives for our apps. In the next section, we'll give a quick introduction to fault tree analysis with a few examples of how to apply it. After that, we'll have the foundation to get to the meat of this talk, which is to create fault trees for Flink. Next, we'll distill our findings into a calculator that you can use as a shortcut to help you gut check what you're signing up for. And finally, we'll conclude with a summary and talk about future work that we think should be done to make Flink more reliable. For Salesforce, security and trust are always our top priority. Part of keeping our software secure and reliable for our customers is being able to be very fast at detecting problems. We use Flink to ingest tons of data from unstructured sources such as our application and machine logs. We process that data, detect anomalies, and generate alerts for internal teams and software systems. In addition to these use cases, it is worth mentioning that we also do machine learning model training, but that doesn't yet require quite the same attention to reliability. The first step when you try to make a system reliable is to ask yourself, what do the system's users need? What will cause the users to think that your solution isn't working? For our critical use cases, we boil it down to two things. One, we must process all data. We can't miss any data points because they could cause us to miss an anomaly or generate a false alarm. Two, we want minimal delays. Once data is created and starts flowing through our systems, we'd like to process it and alarm, if necessary, within seconds. The second step is to create service-level objectives. A service-level objective, or SLO, represents a measurement that we target in order to meet the goals of our users. If this is your first time about hearing about SLOs, I recommend reading the Site Reliability Workbook. Chapter 13 of that book is a great resource that talks about data processing SLOs. We can boil down our goals to two SLOs. One, we'll call it data correctness. We want to process every single item of data for our use cases that require at least once or exactly once processing guarantees. Generally speaking, it is recommended to count how many messages you are processing, perhaps with another Flink app. At most, once processing means that you can skip over data in order to process more recent data. The second SLO we'll call data freshness. We want to alarm when we fall behind too much in processing. We usually keep track of event time and see how far away it is from the processing time. Let's take our two SLOs and establish what we'd like to provide our users as an example. Our use cases are at least once, so we have to say that our data completeness is greater or equal to 100% unique messages processed within a specific time period, in this case 7 days. For exactly once, we change this to exactly 100%. For data freshness, we say 3.5 nines and less than 1 minute delayed. This gives us an error budget of about 5 minutes within the stated 7-day period, or roughly 5 1-minute outages. Before we explore what it takes to achieve these SLOs, let's learn about fault tree analysis. Fault tree analysis is a deductive failure analysis. It was developed in the 1960s at Boeing when it was developing the Minuteman ICBM launch control system. The technique turned out to be really useful and has since been applied in the aerospace, military, petrochemical, pharmaceutical, and other industries that deal with high stakes and hazards. It is a top-down technique whereby you start with a general failure such as ICBM exploded before launch and map it out to contributing components that could have caused that failure. I learned about this technique from Emil Stolarski at a talk he gave at SREcon in 2008. To get started with fault tree analysis, we need to define a few terms and symbols. The first is a top event. This is what we'll call our goal and later our SLO. For us, it is the time that our software is not working. The second is an intermediate event. These are components of the system that might fail and cause other events to occur. For example, hard drive fails, which causes computer to fail, which causes website to go down. Computer failure, in this example, is the intermediate event. The third symbol is a basic event. A basic event is something bad that happens with a probability, such as a hard drive going down. The fourth event symbol is an external event. These are events that are routine, but can contribute to a failure. These are generally deterministic events like a deploy or a software upgrade. These are deterministic because we control when they happen. The last symbol is a transfer event. You can think of it as a programming language function. Fault trees can get very large, and this symbol will be very useful to create groups of subsystems. The next set of symbols are gates. We'll use OR and AND gates in this talk. Ever taken a probability course, you might have found these formulas when you want to determine the probability of 2 or more events occurring. For the OR gate, we'll often take a shortcut and not subtract the product of the probability of A and B because that number will be negligible if the probabilities are small. Let's try to build a fault tree for a stateless web service as a warm-up exercise. In this example, our top event is that our end user sees a connection timeout. We have 2 stateless instances that have a random failure rate of 10%. That means that our end user should see a 1% chance of failing to make a connection. This is because if one of the instances goes down, we're still okay because the other instance is still up and we'll route to it. We'll only fail if both instances are down, and to get that, you multiply the probabilities of these 2 instances to get 1% chance of failure. We can add 5 instances for a total of 7, and you can see that our failure rate will get reduced substantially. In this talk, when the failure probability is really low, fraction of a percent, we switch to thinking of it as a chance of success. We can map this to an availability SLO. In other words, we can call this 5 nines of availability, which is a very strong availability guarantee. Instance failures aren't the only things that might cause our connections to fail. Networking problems might occur because a load balancer usually sits between our application, between our instances and our end user. If we assume a 5% chance of failure for our load balancer, then we have a higher probability failure because the load balancer fails or one of the instances fails. This is where we apply the OR gate. In this example, we have two load balancers, both of them redundant, where we use an AND gate. Note that we've added a transfer event to denote that we have a second load balancer. There are other contributing factors that we could add to this tree, such as DNS, network switch and router failure, and many others. In the interest of time, we'll leave our web app at just instances and load balancers and move on. Now that we have some basics under our belt, let's see what happens when we build a fault tree for a Flink app. To start, we'll assume just one job manager and one task manager. A Flink app needs to get data from somewhere, and unless we make it generate its own data, we usually read from at least one source. Since Kafka is well understood, and because we're heavy users of it, we've put it down as our example source. We'll assume that Kafka has 3.5 nines of availability, and we have network problems occasionally when we try to connect to it. We get about a 0.051% chance of our data source failing, which would cause us to stop processing. On the right side of the tree, our single job manager and task manager can go down because they are on a machine that has a 1% chance of failure. Overall, our Flink app will fail 2.051% of the time as determined by our failure time period, which for the duration of this talk we'll assume is 30 days. If we have multiple data sources that we're reading from, we won't be able to guarantee the same level of reliability. If you are reading from two distinct Kafka clusters, you will need to add or their failure probabilities in the fault tree. Another thing to consider is whether we should factor in the reliability of our syncs. If a sync is down, our Flink app will stop processing and we'll need to wait for it to come back up. However, our syncs themselves ideally will own their own SLOs, and they architecturally depend on our Flink app. In other words, syncs are downstream of Flink, and it would be a circular dependency if we were to add syncs to our Flink application fault tree. To guard against job manager failure, we will either set up HA job managers that talk to a Zookeeper ensemble, or we rely on something like Kubernetes to quickly restart the job manager on a healthy available host. We'll assume Zookeeper-based HA setups in this presentation. For the Kubernetes option, I would encourage you to create a fault tree for Kubernetes itself and understand the probability that Kubernetes will be down when your failed job manager needs to be replaced. As you can see, compared with the single non-HA job manager a couple of slides ago, we improved our reliability by a whole percentage point. Let's now try to do the same for our task manager. This is where it gets really confusing. Notice that we tried to add multiple task managers, 3 in this example. However, we became less reliable when we did that, from 1% chance of failure to 3% chance of failure. The problem is that Flink jobs are distributed among all available task managers, assuming you have more than one task that your job is parallelized with. If one task fails because a task manager goes down, your entire job restarts, and we resume from the last known checkpoint. This is the default behavior, and you can mitigate it somewhat by configuring failover regions. If we view task managers from the lens of a stateless web app, we'll never achieve high levels of availability as we scale. For example, if we vertically scale our task managers and thus have very few of them, we'll be in better shape, but as we scale to larger data volumes, we'll have no choice but to add more Flink task managers because you can't vertically scale forever. The major selling point of Flink is the ability to scale up to very large data volumes. We have to assume that failures will happen more often at higher scale, and the best we can do is to get our app running again as quickly as possible. We need to quantify our recovery times and keep them as short as possible. In this example, we suffer 2 failures. Each failure makes us fall behind our source because the failure causes us to stop processing. If data continues to flow in, the age of data goes up. In the first failure event, we are down for about 6 seconds. We come up and start processing data that is 6 seconds old because that is how long we were down. We then start reading data again at 2x the rate that we read it before, and thus catch up in another 6 seconds. I'll explain in a little bit why the data rate is 2x. We have a second fault that occurs shortly thereafter, but it lasts a lot longer, and thus our recovery is also a lot longer. The age of data that we process is one proxy metric that we can use to determine our data freshness. Depending on your use case, we might need to define your data freshness more rigidly and account for the time it takes to process the data and persist it to your sink, as well as your window durations if you're doing window data processing. Here is what happens when your consume rate is the same as your upstream produce rate. This is a common mistake that is made when your Kafka admins introduce quotas. In the previous example, reads were allowed at double the rate. In this case, read is configured to be the same rate as write. We will never be able to keep up after the first failure if our produce rate is maxed out. In this example, we get lucky because our upstream producer started writing at a lower rate than the quota, and we started catching up. Generally, setting the consumer quota to be 2x greater than your produce quota is advisable. If you want faster recovery, provision more read capacity so that your consume can catch up faster. Here we show a common nightmare scenario with Flink. This usually happens when you complete a security review and realize that you need to apply security patches to your task managers, job managers, and zookeepers. The restarts, if not spread out or coordinated appropriately, will result in you falling behind for very long durations of time, particularly if you have hundreds of task managers. In the Kubernetes world, you'll have 2 sets of restarts because patching needs to be done on the Kubernetes nodes as well as your Flink containers. The previous diagrams don't take account Flink checkpoints. If you're using a source such as Kafka, it is important for you to configure checkpoints because when a body of work is completed, we persist our state and resume from the point at which we left off, persisting. In other words, if you don't enable checkpointing, you'll lose data. In fact, you can consider that your data correctness SLO is being met so long as you don't remove checkpointing, or if you don't rename any of your Flink operators. In steady state, assuming that your checkpoint duration is consistently 5 seconds, you'll see your app fall behind for 5-second intervals and catch up. This is because Flink stops making progress during checkpointing and starts back up. If a fault is combined with our checkpoint configuration, then we see compounding delays. In this example, our fault occurs at second 51, and we aren't able to restart the job for about 15 seconds. Our fault happened at the worst possible time here because our checkpoint was close to completing, but didn't quite make it. We thus have a 5 plus 15 second delay instead of just a 15-second delay. It takes us 37 seconds to get fully caught up, though, because we need to interrupt our processing with 3 additional checkpoints in between. Tuning your checkpoint intervals and timeouts can be a fine art, but it is crucial if you want to reduce your recovery times. Another compounding effect is that the more data you have to catch up to, the longer the duration of your checkpoints. The durations of your checkpoints will depend on numerous factors. Your data volumes, whether your sinks are latent and back pressuring, and your checkpoint store itself can also be slow. For example, your S3 bucket can get throttled. Note that checkpoints don't always take the same amount of time. Since we are trying to get an accurate figure for our recovery speed, this is a problem. Let's posit a simplifying assumption, that our checkpoint durations are a normal distribution. I encourage you to plot a healthy sample of checkpoint durations on a plot like this. The sigma symbol is the standard deviation. Most of your checkpoints will complete within one standard deviation of your average. Occasionally, you'll be within 2 standard deviations, and very rarely more than 2.5. If you're ever wondering about what you should set your checkpoint timeout to, you might want to set it to your average plus 4 to 6 times your standard deviation. Let's now consider our fault tree, or reconsider our fault tree. Instead of just discrete failures, let's assume that failure is defined as events that take more than a certain amount of time to occur. Recall that our Freshness SLO has a time boundary. This diagram is hard to process all at once, so let's start with the job managers. If a single job manager goes down, no big deal, because Zookeeper, assuming it is also not down, will quickly elect another one to take over. Really, we're only in trouble if both job managers are down at the same time. The odds of that are a fraction of a percent, and effectively we have 4 nines chance of success for our Zookeeper with our new duration-based time failure metric. Let's look at our task managers. On the bottom left, we'll assume that we follow best practices and leave a couple of spare task managers idling and ready to take on load if a task manager fails, and there is a job interruption. We'll be more than a minute delayed if both spares are down and job is interrupted. On the right side, we determine a 10% chance of a job interruption if we have 3 active task managers and Zookeepers. We can factor in a 5% chance that humans will make a deployment within a 30-day period, which we can reduce by putting a change moratorium in place. Finally, if a poison pill is injected, usually upstream of Flink, you'll also likely be down for more than 1 minute. Examples of a poison pill is a bad upstream schema change, malformed data injection from a user, or your red team is just messing with you. There are probably more things that can go wrong, but these are the major things that I've seen that have wreaked havoc in the past. The last part of our new and refreshed fault tree are factoring our checkpoint times. We have to determine our average and standard deviation, also known as sigma. We use that to both inform the behind us value on our service level objectives, as well as the probability of exceeding that behind us time. Depending on the load on our system and based on how much state needs to be checkpointed, it might not be possible to have checkpoint plus recovery time fit within 1 minute. Also, consider that your checkpoint store, usually S3, can fail on you. We might also get DDoSed, although I hope that you have Kafka quotas enabled in order to guard against that. Various other factors can cause your checkpoint duration to be too high, including something as simple as not monitoring and tuning your checkpoint settings in response to increasing data rates and code changes to your app. It takes a bit of effort to draw out a fault tree, but most of the time there is no need to go through the full effort in practice. Let me show you how to shortcut it by building a formula that takes information about your Flink app and infra as inputs. This won't be an algebra lesson, I promise. In order to build up the formula, I need to build up some context. These are a set of steps that you can employ to set yourself up for success. Let me walk you through each of them. Most of us start with a proof of concept where we evaluate the functionality and make sure that Flink will work end-to-end in our infrastructure. You'll want to observe your app's behavior when you push your environment to its limits. We want to push more data than we expect to process at full scale, and observe how your checkpoint times change with that. Also, stress your resources. Squeeze your task managers by running fewer of them. Downsize your job manager. Also, pause the app for 1 hour and restart it. Make sure that you can catch up with a rate that is at least 2 times your maximum produce rate. To get an accurate checkpoint average and standard deviation, 100 to 200 data points should generally cover a day or two of running your Flink app. However, if you want to be rigorous, you can reverse the traditional confidence interval statistical equation and run it on this formula. N is the sample size of checkpoints you will need to consider to have confidence in your checkpoint data. Z star can be looked up in a table on Wikipedia. Knowing how often you'll need to apply security patches will help you determine how many job interruptions you should expect. Another input you'll need to keep an eye out for is how often you have network and node failure faults. Different compute providers will have different annualized failure rates, or AFRs. The probability that a node will go down in a 30-day period is the AFR divided by 12 multiplied by the number of job interruptions and checkpoint interval plus durations divided by the number of time units in a 30-day period. Always make sure to use the same time units. The toughest foe that you will likely have are poison pills. Try to inject malformed data upstream that your Flink app will choke on and see how long it takes you to recover. I've seen poison pill takes anywhere from several hours to multiple days to resolve. The better you are prepared for them, the lower your mean time to recovery is going to be. If you've put in place measures to avoid them, such as version topics, quality control environments, or schema registries, then your expected number of poison pills will be lower. Finally, we're ready to see the formula. I tried to list each variable only once. One important thing to note is that we're selecting 3 standard deviations as our checkpoint duration. Why? This allows us to have confidence that we'll rarely fall behind by the threshold. A lot of us in the industry operate on 30-day SLO periods. So to avoid adding more variables, we'll just assume 30-day period. Let's apply it to an example with 20 task managers, checkpoint durations in intervals of 5 minutes, 60-minute MTTRs for poison pills, and monthly security patching. We get that we can stay within 20 minutes 99.44% of the time in a 30-day period. This is fairly conservative because it gives you a total error budget of about 4 hours each month. This is a good thing, however, because you'll likely underpromise and overdeliver for your users. Here's a chart showing what happens when we adjust various factors. This is equivalent to changing rates of failures in our fault tree. If we increase the number of our task managers, we lose half a 9 of reliability. If we see higher failure rate of nodes, we lose about that much as well. If we change our security update to be weekly, the extra restarts cause us to reduce our SLO. If you want to switch to 1 sigma, or 1 standard deviation, to set your freshness threshold, you now substantially reduce how often you will be within the threshold. Doing 5 deploys per day instead of 1 will also reduce your thresholds. Finally, if you change your units to seconds instead of minutes, you can't guarantee as easily that you'll be under 20 seconds. The bounding factor there is that your poison pill probability and recovery time. If you remove that, then you'll be better off and almost equivalent to if you are operating in SLOs in the order of minutes. Your journey never ends so long as your Flink app is in service. Revise your SLOs regularly, and don't forget to tune your checkpoint settings as your data volumes increase. If you dozed off or simply skipping around on this video presentation, this is where you might want to shake yourself awake and absorb the key findings from our research. At the beginning of this presentation, we had stringent requirements in mind. We've discovered that we can meet them, but we have to take care of a lot of items, especially as we scale. Flink has counterintuitive scaling properties if you are coming from a stateless application or stateful storage background. Your reliability will go down if you horizontally scale with smaller instances. It is better to scale your instances up, that is, run larger instance types and then scale horizontally. Reducing the number of components in your system is always a win for reliability. Third, when you do security upgrades to your infrastructure that Flink runs on top of, it is often better to scale up your instances, then bulk destroy the old ones. This results in one restarts versus many and shortens the overall time that your application is not processing. With any system, we have to worry about reducing the number of failures that happen as well as reducing the duration of those failures. However, if you want to exactly once or at least once processing to happen, which is what a lot of us rely on in the data world, you'll find that your failure durations cascade into a vicious cycle where the longer the failure, the longer the recovery time will be. Similar to rocketry, where if you add more weight, you need to add exponentially more fuel. In our case, more automation. Looking to the future, we first need to explore how state size growth impacts our recovery times. If you are using S3 as your checkpoint store, your checkpoint times take really long due to throttling backtrack pressure. These long checkpoint times will cause you to fall behind and breach your SLOs from time to time. It would be great to do more research into precursors that might cause this and how to avoid this problem. Local task recovery helps reduce recovery times and makes Flink resume processing faster. However, there isn't a clear rubric for when recovery for the remote store is needed. For example, if you do immutable upgrades with Kubernetes, you can't recover locally, but if you do in-place reboot upgrades, you should be able to recover locally. According to the Flink user mailing list in August 2021, it doesn't appear that in-place upgrades will work. This is something to explore further once the issue is resolved. Measuring our SLOs accurately is another challenge that we can get better at. Oftentimes, data completeness isn't really measured at all because you need to build infrastructure in order to measure it. Counting individual records passing through is not enough. These records themselves can be duplicated at the source, which will break exactly one's processing if you're not careful. This would be a form of garbage in, garbage out. For this presentation, I had limited data, and I'm curious if with enough data we discover that checkpoint times don't follow a normal distribution. Perhaps it is a skewed distribution or something else entirely. It is possible that different Flink use cases might result in different distributions. Finally, there are new Flink features that may or may not improve things. One obvious one is unaligned checkpoints. We effectively allow processing to take place in the midst of a checkpoint. I'm excited to watch this feature get rolled out in production workloads and see how it impacts recovery times. Here is a summary of some papers and presentations that I alluded to. You can visit github.com/afalco/ftaflink in order to click on any of these links, as well as view these presentation slides. Finally, the last parting message I'd like to convey is that we're hiring. Connect with me on LinkedIn, and I'll be happy to refer you to the right role and manager. I wouldn't have worked at Salesforce for 9 years and have rejoined it recently if it weren't an amazing place to work. We'll be thrilled to innovate with you. Thank you all very much.